The air is so still here that I can hear my own breath becoming visible, transforming into tiny crystals of ice that catch the pale Antarctic light and drift slowly downward like the smallest of snowflakes. I've traveled to the edge of the world, to a place where time itself seems to have slowed down, pooled, and frozen into something you can touch, something you can read like the pages of an ancient book. This is the ice. I stand at the entrance of our small research station, watching the sun make its long, lazy arc across the horizon, never quite setting, never quite rising, just endlessly circling in this season of perpetual twilight. The sky above me holds colors that don't seem to exist anywhere else on Earth. Soft lavenders bleeding into pale greens, hints of rose gold touching the edges of thin, high clouds made of ice crystals so fine they seem more like thoughts than weather. The cold here is different from any cold you've experienced before. It's not the biting, aggressive cold of a winter wind back home. This cold is patient, ancient, and somehow peaceful. It wraps around you gently, reminding you that you're standing on ice that's 2 miles thick beneath your feet. Ice that's been accumulating layer by layer for hundreds of thousands of years. Every snowflake that fell here stayed, compressed slowly by the weight of time into a crystalline archive of Earth's history. I'm a glaciologist, and I've spent years learning to read this frozen library, but tonight, as the station settles into its quiet evening rhythm, I'm not thinking about data or research papers. I'm simply here, present in this moment, feeling the profound stillness that exists at the bottom of the world. My colleagues have retired to their quarters, and I volunteered for the evening observation shift. A few hours of peaceful solitude in the observation dome, watching the ice and sky perform their slow dance together. The snow beneath my insulated boots squeaks with each step I take. It's a sound you only hear in extreme cold, when ice crystals are too frozen to melt even slightly under pressure, when they can only crack and shift against each other with that distinctive, almost musical protest. I pause and listen to the silence that follows. True silence, the kind of quiet that exists when you're hundreds of miles from any city, any road, any tree, any sound of human civilization except for the small outpost behind me. I make my way slowly toward the ice core storage facility, a structure half buried in snow to keep it at constant, stable temperatures. The sky is beginning to shift now, and I feel that familiar tingle of anticipation. The instruments predicted it earlier today. Tonight, we might see the aurora australis, the southern lights. But even if we don't, even if the sky remains clear and still, there's something profound about being here, being present in this landscape of ice and silence. As I walk, I think about what lies beneath me. The ice sheet here is ancient, beyond easy comprehension. If I could drill down through it, and we have in several locations, I would pass through layers that fell as snow during the last ice age, during the medieval period, during the time of ancient Rome, during the age when humans first learned to make fire. Deeper still, through ice from before humans existed at all, when the earth was in different configurations of cold and warm, when the very composition of the atmosphere was subtly different from today. Each layer is a page in Earth's diary, and it remembers everything. Trapped in those layers are tiny bubbles of ancient air, perfectly preserved, waiting to tell us what the atmosphere was like thousands of years ago. Volcanic ash from eruptions that shaped human history, cosmic dust from meteor showers long forgotten, even pollen grains from plants that grew on distant continents, carried here on high-altitude winds, and settled grain by grain into the accumulating snow. The observation dome rises before me, its curved, transparent panels already beginning to show a faint reflection of green light in the northern sky. My heart lifts gently. Yes, tonight we'll have auroras. I enter through the double doors, carefully sealing each one behind me to maintain the temperature inside, and climb the short ladder to the observation platform. Here, surrounded by windows on all sides, I have an unobstructed view of the ice plateau stretching endlessly in every direction, and above it, the vast dome of the polar sky. I settle into the cushioned observation chair designed for long hours of comfortable watching and allow my eyes to adjust to the gathering darkness. Not true darkness. In Antarctica during this season, darkness never fully arrives. Instead, the world transitions into shades of deep blue and purple, with the ice reflecting back whatever light the sky offers. The aurora is beginning now, starting as it always does with a faint glow on the horizon, like the first hint of dawn, but in the wrong direction and the wrong color. Green light, soft and diffuse, as if the sky itself is slowly waking up. The green glow strengthens slowly, patiently, in the way that all things happen here. Nothing rushes in Antarctica. I watch as the light begins to take shape, forming a gentle arc that stretches across perhaps a third of the visible sky. It reminds me of a curtain caught in a breeze so subtle you can barely perceive the movement, and yet the fabric ripples and flows with undeniable grace. I let my breathing slow to match the rhythm of the aurora's movement, in as the light brightens slightly, out as it fades to a whisper, in as new tendrils of green reach upward, out as they dissolve back into the darkness. This is one of the things I've learned here in this place of profound patience, that observation itself can become a form of meditation, a way of syncing your own small human rhythms with the larger rhythms of Earth and sky and cosmos. The aurora australis, the southern lights, is born from the same physics as its more famous northern cousin, the aurora borealis, but somehow it feels more secret, more intimate, witnessed by so few. What I'm watching is the visible result of an invisible collision, charged particles from the sun, riding the solar wind across 93 million miles of space, finally encountering Earth's magnetic field. The field guides these particles down toward the poles, funneling them like water spiraling toward a drain until they collide with oxygen and nitrogen molecules in the upper atmosphere. Those collisions transfer energy, and that energy must go somewhere, so it becomes light. The green I'm seeing now comes from oxygen atoms about 60 to 150 miles above me, excited by the impact of solar particles, releasing their extra energy as photons in that particular shade of luminous green. If the particles strike higher, where oxygen is less dense, they produce red light instead. Lower down, where nitrogen is more abundant, we see purples and blues, though these are rarer, more fleeting. But knowing the physics doesn't diminish the magic. If anything, it deepens it. I'm watching a conversation between the sun and the earth, mediated by magnetic fields that stretch far out into space, creating an invisible architecture that shapes and guides and protects. Without Earth's magnetic field, the solar wind would have stripped away our atmosphere billions of years ago, the way it stripped away Mars's atmosphere, leaving that world cold and dry and silent. The aurora is a reminder that we live inside a protective bubble, a magnetic embrace that makes all life possible. The curtain of light is dancing now more actively, and I notice hints of pink beginning to appear along its lower edges, that rare red-violet combination that happens when the solar wind is particularly strong. I feel privileged to witness this. Each aurora is unique, never to be repeated exactly. The specific pattern of solar wind, the precise state of Earth's magnetic field at this moment, The particular mixture of atmospheric gases at various altitudes, all of these variables combine to create this one unrepeatable performance. I shift slightly in my chair, keeping my movement slow and gentle, and reach for the thermal flask of tea I prepared before coming here. Chamomile, with a hint of honey, still warm. I pour a cup and hold it in both gloved hands, feeling the warmth through the insulated fabric, watching the steam rise and immediately begin to freeze into tiny ice crystals that sparkle briefly in the aurora light before settling onto my jacket. The ice outside is responding to the aurora too, in its own way. The snow surface, sculpted by wind into subtle waves and ripples called sastrugi, catches and reflects the green light, transforming the entire plateau into a ghostly mirror. It's as if the earth is trying to reach back up to touch the sky, to complete some ancient circuit between ground and atmosphere and space. I think about the cores we've extracted from this ice, cylinders of frozen time, some of them more than 2 miles long, representing 800,000 years of continuous climate record. We store them in the facility I passed on my walk here, kept at perfect preservation temperature, available for researchers from around the world to study. Each core is carefully marked, cataloged, describing exactly which depth it came from, which year or millennium it represents. When we analyze these cores, we're doing something that would have seemed like magic to people just a century ago. We're directly sampling the ancient atmosphere. Those tiny air bubbles trapped in the ice are time capsules, perfectly sealed, containing the exact mixture of gases that existed when the snow first fell. By extracting these bubbles carefully and analyzing their contents, we can measure the concentration of carbon dioxide, methane, and other gases going back hundreds of thousands of years. The ice tells us stories of warmth and cold, of ice ages and interglacials, of volcanic eruptions that dimmed the sun and disrupted agriculture across entire continents. We can see the Industrial Revolution written in the ice as clearly as words on a page, the sudden spike in carbon dioxide and other gases beginning around 1850, when humanity began burning fossil fuels at scale. We can see evidence of Roman lead smelting, of ancient forest fires, of changes in ocean temperature reflected in the isotopic composition of water molecules themselves. But tonight, I'm not analyzing. Tonight, I'm simply here, a witness to beauty, a small conscious being sitting on an ancient sheet of ice, watching light dance overhead in the thin air of the upper atmosphere. The aurora has grown more complex now, with multiple curtains overlapping, some brighter than others, all shifting and flowing like luminous kelp in a cosmic ocean. I take a slow sip of tea and feel the warmth spread through me. The contrast is delicious. The cold air on my face, the warm liquid inside, the interplay of temperature and comfort. I'm dressed in layers, as we always are here, thermal underwear, fleece mid-layers, an insulated outer jacket, boots rated to -60 degrees Fahrenheit, though it's much warmer than that tonight, perhaps only -20. The station behind me is a small constellation of warm yellow lights, windows glowing against the blue twilight. I can imagine my colleagues inside, Sarah probably reading in her bunk, Marcus likely reviewing tomorrow's drilling schedule, Chen perhaps writing in his journal as he does every evening. We're a small community here, 7 people currently, though the number varies with the season. In the depths of winter, when flights are impossible and the continent is completely isolated from the rest of the world, we'll be down to just 4. The thought of winter isolation doesn't frighten me. Instead, it brings a sense of peaceful anticipation. There's something profoundly restful about knowing that for several months we'll be truly unreachable, held gently in Antarctica's embrace with no possibility of leaving, no pressure to be anywhere else. We'll have everything we need: food, fuel, each other's company, and this vast library of ice to study and contemplate. The aurora is shifting again, and now I notice something remarkable happening. The green curtains are beginning to pulse, brightening and dimming in waves that travel along their length like slow, gentle heartbeats. Scientists call this pulsating aurora, and it happens when the processes generating the light undergo rhythmic changes, though the exact mechanisms are still not fully understood. There's something humbling about that, about being a scientist surrounded by instruments and data, and yet still encountering phenomena that hold mysteries, that remind us how much we have yet to learn. I let my gaze soften, not focusing on any particular point, but taking in the whole sweep of sky and ice and light. This is a technique I learned from an astronomer friend. Sometimes the best way to see is to stop trying so hard to look. The human eye has two types of light receptors: cones for color and detail, concentrated in the center of our vision, and rods for dim light and motion detection, spread more widely across our retina. In low light like this, the rods are more sensitive, but they work best when we're not staring directly at something. So I let my vision relax, and the aurora becomes even more vivid, more alive. The ice beneath the station is moving, though far too slowly for me to perceive. The entire East Antarctic ice sheet is flowing outward from the center of the continent toward the coast, driven by its own immense weight, moving at rates measured in meters per year. It's a glacier, the largest glacier on Earth, though it doesn't look like the dramatic ice rivers you see in mountain regions. Here, the movement is stately, patient, inexorable. The ice I'm sitting on will eventually reach the coast, perhaps 100,000 years from now, where it will break off into the ocean as an iceberg and begin its slow journey northward into warmer waters. But that's a story for a different time scale. Tonight, in human time, everything is still, or almost still. I tune my hearing to the ice and realize I can hear it. Tiny sounds, barely audible, like distant whispers or the creaking of an old ship. These are the sounds of the ice sheet adjusting to temperature changes, to its own weight, to the imperceptible stresses that accumulate and release in movements too small to see but just large enough to hear if you're listening carefully. The tea is cooled now, but I finish it anyway, savoring the last warmth. I think about water, about how this simple molecule, two hydrogen atoms bonded to one oxygen atom, is the most important substance for life as we know it, and yet it's also the substance that has written Earth's history in ice. Water is unusual, strange even in its properties. Unlike almost every other substance, it expands when it freezes, which is why ice floats and why this continent exists as it does, why lakes freeze from the top down rather than the bottom up, allowing life to persist beneath winter ice. Water also has an extraordinarily high heat capacity, meaning it can absorb and store large amounts of heat without changing temperature much. This is why oceans moderate Earth's climate, why coastal regions have milder weather than continental interiors, why our planet doesn't experience the wild temperature swings that occur on worlds without liquid water, and water's ability to exist in all three states, solid, liquid, gas, at temperatures common on Earth's surface, makes it the perfect vehicle for moving energy and matter around our planet through the hydrological cycle. The ice here in Antarctica represents about 70% of Earth's fresh water. If it all melted, which it won't, not on any time scale relevant to human civilization, though parts of it are indeed changing, sea levels would rise by nearly 200 feet. Every coastal city would be transformed. the map of the world would be redrawn. This is why we're here, studying this ice, learning to read its history, trying to understand how it has responded to climate changes in the past so we can better predict how it might respond in the future. But these thoughts, important as they are, feel too heavy for this moment. I gently set them aside and return my attention to the aurora, which has now spread across more than half the sky. New colors are appearing, hints of purple along the upper edges, suggesting that the solar particles are penetrating deeper into the atmosphere than before. The whole display seems to be intensifying, and I feel a quiet thrill of gratitude that I'm here to witness it. In ancient times, people who saw auroras, mostly those living in far northern regions, created myths to explain them. The Vikings thought they were reflections from the shields and armor of the Valkyries, warrior maidens who chose which soldiers would die in battle and escorted them to Valhalla. Some indigenous peoples of North America believed they were the spirits of ancestors dancing in the sky. In medieval Europe, they were sometimes interpreted as omens of war or disaster, blood in the sky predicting bloodshed on Earth. Now we know the physics, the mechanisms, the precise chain of cause and effect, stretching from nuclear fusion in the sun's core to excited oxygen atoms glowing green in Earth's thermosphere. But somehow, the auroras remain no less wondrous. If anything, understanding their origin makes them more beautiful, because now we can appreciate the vast scales involved, the 93 million-mile journey of solar particles, the protective magnetic field generated by flowing molten iron in Earth's outer core thousands of miles beneath my feet, the delicate atmospheric chemistry that transforms particle collisions into visible light. Science doesn't diminish wonder. It multiplies it, deepens it, reveals layers of complexity and connection that make the universe more marvelous the more we understand it. I feel this truth settle into me as I watch the dancing lights, a sense of peace and rightness about being here, about being a curious human on a beautiful planet, trying to learn its stories. The observation dome is perfectly quiet except for the soft hum of the heating system maintaining a barely tolerable indoor temperature. Outside, it must be even quieter, the kind of silence that only exists in places far from civilization, far from wind, far from life. Antarctica, in calm weather, is one of the quietest places on Earth. Sound recordings made here pick up almost nothing, just the faint whisper of snow crystals shifting, the occasional crack of adjusting ice, and sometimes, if you're very lucky, the low-frequency rumble of an ice quake, when stress accumulated over years or decades suddenly releases. I set down my empty cup and noticed something unusual in the ice below. A faint line of blue-green luminescence tracing through the snow about 50 meters from the dome. At first, I think it might be a reflection of the aurora, but it's too localized, too specific. My curiosity pulls me to my feet. This is something I haven't seen before in my 3 months at the station, and in Antarctica, anything unusual deserves investigation. I make my way down from the observation platform and prepare to go outside, double-checking my equipment. Even a short walk requires preparation here. I activate the small radio beacon on my jacket. Protocol requires that any time someone leaves the station alone, and step through the double doors into the crystalline cold. The glow is still visible, and as I approach, I realize what I'm seeing. A peculiar formation of ice that's catching and channeling the aurora light in an unexpected way. But more than that, there's bioluminescence. Here, in Antarctica, on the surface ice. I kneel down carefully, my headlamp revealing a thin film of what appears to be cryoconite, dark sediment containing microorganisms that have adapted to live in the most extreme environment on Earth. But this particular patch is doing something extraordinary. It's glowing with a soft blue-green light of its own, completely independent of the aurora above. My mind races through the possibilities. I'm likely looking at psychrophiles, organisms that thrive in extreme cold, but bioluminescent ones are exceptionally rare in Antarctic surface environments. Most bioluminescence here exists in the ocean beneath the ice shelves, where strange fish and jellies produce light in the eternal darkness. But this is different. I pull out my sample collection kit, moving with practiced efficiency despite my bulky gloves. If these are indeed bioluminescent bacteria or algae surviving on the surface ice, they represent an adaptation that could have profound implications. Life finding a way to generate light, which requires significant energy, in an environment where every calorie is precious, where temperatures regularly drop to -40 degrees, where months pass without sunlight. This is evolution's creativity at its most remarkable. As I carefully collect a sample into a sterile vial, I think about the extremophiles we've discovered in recent decades. Life on Earth exists in places we once thought impossible. In boiling acidic hot springs, in rocks miles beneath the surface, in the dry valleys of Antarctica, where it hasn't rained for millions of years, even in the cooling pools of nuclear reactors. These discoveries have revolutionized our understanding of life's limits, or rather, revealed that life has far fewer limits than we imagined. One of the most remarkable findings came from Lake Vostok, a subglacial lake buried beneath 2.5 miles of ice, about 400 kilometers from here. It's been sealed off from the surface for 15 million years, existing in complete darkness under enormous pressure. When we finally managed to sample its waters, an engineering feat that took decades, we found it teeming with microbial life. Bacteria that had evolved in total isolation for longer than modern humans have existed, developing unique metabolic pathways, living off the chemistry of rock and water rather than sunlight. These extremophiles have changed how we think about life elsewhere in the universe. Europa, one of Jupiter's moons, has an ocean beneath its icy shell that might be twice the volume of all Earth's oceans combined. Enceladus, a moon of Saturn, shoots geysers of liquid water into space from an underground ocean. If life can thrive in Lake Vostok, why not in the dark oceans of Europa or Enceladus? The principles would be the same. Liquid water, chemical energy, time. I seal the sample and stand, my knees protesting slightly from kneeling on the ice. The aurora above has reached its peak intensity now, with curtains of green and pink and purple undulating across 3/4 of the sky. The light is bright enough that I can see my shadow on the snow. Multiple shadows, actually, each cast by a different section of aurora, all moving and shifting as the lights dance. I make my way toward the ice core storage facility, deciding to check on something while I'm out here. The samples I've just collected will need to be processed carefully, kept cold but not frozen, given to Chen, who specializes in microbiology. But first, I want to see one particular ice core that arrived from a deep drilling site just yesterday, a section from 1.2 million years ago, the oldest ice ever recovered from Antarctica. The storage facility is kept at -36 degrees Celsius, cold enough to prevent any degradation of the ice, but warm enough that we can work inside for short periods without excessive discomfort. I enter through the airlock, my breath immediately becoming a thick fog in the even colder air, and make my way down the rows of stored cores. Each core is about 10 centimeters in diameter and stored in sections about a meter long, carefully labeled with its depth and estimated age. The facility is essentially a library, But instead of books, it contains frozen time. I find the new arrival, core section 3,941, depth 3,240 meters, age approximately 1.2 million years. Through the clear storage container, I can see the ice itself. And it's beautiful in a way that's hard to describe. It's not clear like surface ice or freezer ice. Instead, it has a deep blue color, almost sapphire, which comes from the way ancient ice under pressure absorbs red light and scatters blue. Air bubbles that were once spherical have been compressed by the weight of ice above them into elongated shapes, and in some sections, they've been squeezed so much that the air has dissolved back into the ice crystal structure itself, forming something called clathrate hydrates, cage-like structures of water molecules with air molecules trapped inside. This ice fell as snow 1.2 million years ago during a period we call the Middle Pleistocene. Homo erectus walked the earth then, but Homo sapiens, modern humans, wouldn't evolve for another million years. The world was in the grip of ice age cycles, but they were different from more recent ice ages. The rhythm was changing, shifting from cycles that repeated every 41,000 years to the 100,000-year cycles that have dominated the past 800,000 years. Scientists call this the Middle Pleistocene transition, and we still don't fully understand what caused it. But this ice remembers. Trapped in its structure is air from that transitional time, and by analyzing it, we're slowly piecing together the puzzle. The leading theory involves feedback loops between ice sheets, ocean circulation, atmospheric carbon dioxide, and the way continents were positioned. Small changes in Earth's orbit, Milankovitch cycles, triggered by the gravitational pull of other planets, alter how much sunlight reaches different parts of Earth at different times of year. These subtle changes can tip the climate into or out of ice ages, but only if various feedback mechanisms amplify the initial signal. I stand mesmerized by the blue ice, holding my gloved hand near the container, but not touching. Even through insulation, my body heat could damage this irreplaceable archive. Inside this frozen cylinder are answers to questions we haven't even thought to ask yet. Each time we develop a new analytical technique, we can return to these cores and extract new information. Ice that was drilled decades ago is still yielding fresh discoveries as our technology evolves. One of the most astonishing recent findings came from analyzing the ratios of different isotopes within the ice itself. Water molecules come in several varieties depending on which isotopes of hydrogen and oxygen they contain. Normal water has 2 hydrogen-1 atoms and 1 oxygen-16 atom, but some molecules have deuterium, hydrogen-2, or oxygen-18 instead. These heavier isotopes behave slightly differently during evaporation and precipitation. When ocean water evaporates, the lighter isotopes evaporate more easily, leaving the ocean slightly enriched in heavy isotopes. When that water vapor condenses and falls as snow, the heavier isotopes condense first. And here's the crucial part. When the world is colder and more ice is locked up in glaciers, the isotopic composition of both the ocean and the snow changes in predictable ways. By measuring these ratios precisely in ancient ice, we can reconstruct past temperatures with remarkable accuracy. Not just the temperature where the snow fell, but global average temperatures, ice volume, even patterns of atmospheric circulation. But perhaps the most exciting recent development involves something called trapped air analysis. When we extract those ancient air bubbles and analyze them with modern mass spectrometry, we're not just measuring carbon dioxide and methane anymore. We can detect trace gases, aerosols, even individual molecules that tell us about volcanic eruptions, forest fires, dust storms, changes in marine productivity, and biological activity across the entire planet. One core sample revealed a massive volcanic eruption about 74,000 years ago, the Toba supervolcano in what is now Indonesia. The eruption was so catastrophic that it may have brought humanity to the brink of extinction, reducing the global human population to perhaps just a few thousand individuals. We can see the volcanic ash layer in the ice, measure the sulfur dioxide that dimmed the sun for years afterward, and track how global temperatures plummeted in response. That genetic bottleneck, that near-extinction event, is still visible in human DNA today. Every person alive is descended from that small population that survived. I carefully note the core's location in my field journal, making a mental note to suggest to our team that we request a small sample for the new bioluminescent organism analysis. If extremophiles can survive on the surface, might there be dormant life trapped in the ancient ice itself? It's not impossible. Scientists have successfully revived bacteria from ice hundreds of thousands of years old, and some researchers claim to have cultured microorganisms from ice even older than that, though those findings remain controversial. The implications are staggering. If microorganisms can survive frozen for 1,000,000 years and then revive when conditions improve, it suggests that life could potentially survive in frozen states for geological timescales. A planet that's currently frozen might have hosted life in a warmer past, with that life now waiting dormant in the ice, ready to revive if conditions change. This idea, called panspermia in its most extreme form, suggests that life, or at least dormant microorganisms, could potentially travel between planets on meteorites, surviving the cold vacuum of space in a frozen state. We know that rocks from Mars have reached Earth. We found them. Martian meteorites blasted off the red planet by asteroid impacts and eventually captured by Earth's gravity. If dormant microorganisms can survive in ice for millions of years, could they survive the journey? Could life on Earth have originally come from Mars, or vice versa? It's a humbling thought that the extremophiles here in Antarctica might be our best clues to understanding how life could spread through the cosmos. I make my way back outside, and immediately I'm struck by a change in the aurora. The curtains have consolidated into an enormous spiral structure centered almost directly overhead, a formation called an auroral corona. It happens when the curtains align with Earth's magnetic field lines in just the right way, creating the illusion that they're all radiating from a single point in the sky, like a cosmic whirlpool or the eye of a vast storm. Standing beneath it, I feel vertigo in the best possible way, as if I'm looking down into an infinite tunnel of green and purple light. The spiral seems to rotate slowly, clockwise, though I know this is partly an illusion created by waves of luminosity traveling along the magnetic field lines. I let myself feel small in a way that's oddly comforting. A single conscious being on a spinning planet, watching the visible evidence of invisible forces that connect our world to the sun, to space, to the larger cosmos. The temperature has dropped slightly, and I notice my breath crystallizing more quickly now, tiny ice diamonds forming in the air before my face. Each exhaled breath contains water vapor from my lungs, and in this extreme cold, that vapor doesn't just condense, it freezes instantly into ice crystals small enough to remain suspended in the air, creating a glittering cloud that catches the aurora light before slowly settling to the ground. These ice crystals are adding to the snow layer that will eventually, thousands of years from now, be compressed into ice and preserve a record of this moment. Somewhere in my breath are molecules that will carry forward in time. Water molecules, yes, but also carbon dioxide, traces of the tea I drank, even a few cells shed from my respiratory system. In a sense, I'm becoming part of Antarctica's archive, my presence here recorded in the slow accumulation of ice. I think about the other traces humans have left in the ice cores. We can see the Industrial Revolution beginning around 1850 with a sharp rise in carbon dioxide and soot particles. We can see the advent of leaded gasoline in the 1920s and its phase out in the 1970s and 80s, written clearly in lead concentrations. We can even see the era of above-ground nuclear testing from 1945 to 1963, marked by radioactive isotopes that don't exist naturally, but were created in nuclear explosions and spread globally through the atmosphere before settling into the snow. These anthropogenic markers, signs of human activity, are so distinctive and globally synchronized that geologists have proposed defining a new geological epoch, the Anthropocene, the age of human influence, and its beginning is written in ice, readable by future scientists, whether human or whatever might come after us. We've become a geological force, capable of altering the planet's chemistry, biology, and even its physical structure on timescales that will remain visible for millennia. But tonight, standing under the aurora with the ice stretching endlessly in all directions, these heavy thoughts feel distant. Right now, I'm simply here, present, a witness to beauty. The aurora corona is beginning to break apart now, the spiral dissolving back into curtains that drift and flow across the sky like luminous kelp in a slow current. The curtains separate and reform, creating new patterns, and I notice something I've read about but never witnessed, a rare phenomenon called STEVE, strong thermal emission velocity enhancement. A narrow ribbon of purple light has appeared, stretching east to west across the sky like a cosmic highway, distinct from the green aurora curtains. STEVE isn't technically an aurora at all, but rather a river of hot, fast-moving gas in the ionosphere, heated to thousands of degrees and flowing at several kilometers per second. The discovery of STEVE is a perfect example of how citizen scientists and professional researchers can collaborate. For years, aurora photographers noticed this purple arc in their images, but assumed it was just an unusual form of aurora. Then, in 2016, a group of aurora enthusiasts brought it to the attention of scientists, who realized it was something entirely new, a phenomenon that had been occurring all along, but had never been properly identified or studied. Satellites passing through STEVE measured temperature increases of 3,000 degrees Celsius and velocity changes of 6 kilometers per second compared to the surrounding air. What excites me about STEVE is what it represents. Despite centuries of studying Earth's atmosphere, despite our satellites and instruments and vast accumulated knowledge, we're still discovering fundamental new phenomena. The universe continues to surprise us, to reveal that our understanding is incomplete, to invite us deeper into mystery and discovery. I start walking, not back to the station, but perpendicular to it, following a marked route that leads to one of our automated weather stations about half a kilometer away. The walk will do me good, give me time to think, and I want to check on the station's instruments. Sometimes ice buildup can affect their readings, and manual inspection is still the most reliable way to catch problems. The snow squeaks rhythmically beneath my boots, and I fall into a meditative pace, breathing steadily, feeling my body warm from the gentle exertion even as my face grows colder in the still air. Above me, STEVE is fading now, the purple ribbon thinning and breaking apart, but the green curtains remain, still dancing their slow dance. As I walk, I think about the ice beneath me and the extraordinary pressure it creates. At the bottom of the ice sheet, more than 2 miles down, The pressure from all that accumulated ice is so immense that it actually lowers the melting point of water. This might seem counterintuitive. We usually think of increased pressure making things more solid, not less. But water is one of those unusual substances with peculiar properties. Under extreme pressure, ice can melt, even at temperatures well below 0 Celsius. This means that at the very bottom of the ice sheet, where it meets the bedrock of Antarctica, there's often a thin layer of liquid water, meltwater created purely by pressure. This water acts as a lubricant, allowing the ice above to slide more easily over the rock. It's one of the reasons glaciers flow at all, and these subglacial lakes and rivers form an entire hidden water system beneath the ice, a dark, cold, aquatic ecosystem that we're only beginning to explore. Lake Vostok is the largest of these subglacial lakes, but we've now identified more than 400 others using ice-penetrating radar. They're connected by rivers, forming a vast network of water flow beneath the ice. And remarkably, they're not static. They fill and drain over cycles of months to years, water flowing from one lake to another through channels carved in the ice or rock. When we finally sampled Lake Vostok's water, a process that required drilling through 3.7 kilometers of ice with meticulous attention to sterility to avoid contaminating this pristine environment, we found thousands of species of bacteria and other microorganisms. They were living in complete darkness at temperatures just above freezing, under pressure 400 times greater than at sea level, cut off from the surface world for 15 million years. These organisms survive through chemosynthesis rather than photosynthesis. They derive energy from chemical reactions involving minerals in the water and bedrock, essentially eating the rock and the water itself. Some of them are likely producing energy through oxidation reactions with iron and sulfur compounds. Others might be using hydrogen as an energy source, produced when water reacts with iron-bearing minerals in a process called serpentinization. This discovery has profound implications for astrobiology. Europa, Jupiter's moon, almost certainly has a subsurface ocean in contact with a rocky seafloor, maintained in liquid state by tidal heating from Jupiter's immense gravitational pull. If chemosynthetic life can thrive in Lake Vostok, why not in Europa's ocean? The conditions would be remarkably similar: darkness, cold, pressure, liquid water, and chemical energy from rock-water interactions. In fact, Europa might be an even better habitat for life than Lake Vostok. The tidal heating that keeps Europa's ocean liquid also creates hydrothermal vents on its seafloor, underwater hot springs where mineral-rich water provides concentrated chemical energy. On Earth, hydrothermal vents host some of the most productive and diverse ecosystems in the deep ocean. Tube worms 2 meters long, eyeless shrimp that swarm in the thousands, mussels, crabs, and countless microorganisms, all thriving in complete darkness, independent of the sun. Some scientists even think that life on Earth might have originated at hydrothermal vents, rather than in shallow sunlit waters. The vents provide chemical energy, shelter from harmful ultraviolet radiation that was intense on early Earth before oxygen accumulated in the atmosphere, and a natural mechanism for concentrating organic molecules. If this hypothesis is correct, then Europa's ocean, with its own hydrothermal vents, might be an ideal cradle for life. I reach the weather station, a sturdy metal tripod bristling with instruments, anemometers to measure wind speed, thermometers, barometers, radiometers measuring incoming solar radiation, and sophisticated sensors analyzing atmospheric composition. Everything appears to be functioning correctly, though there's some frost accumulation on the radiation shield that I brush away carefully with my insulated glove. The station's data logger shows the current conditions. Air temperature, -22 Celsius, wind calm at less than 1 knot, atmospheric pressure 9 out of 84 millibars, and rising slightly. These measurements, along with millions of others from weather stations across Antarctica and around the world, feed into climate models that help us understand how Earth's atmosphere and oceans work as an integrated system. Antarctica plays a crucial role in global climate, acting as one of Earth's great refrigerators. The ice sheet is so cold and massive that it creates its own weather systems. Cold, dense air flows down from the high interior plateau toward the coast. Katabatic winds that can reach hurricane force in some locations, though here in this relatively calm region, they're usually gentle. The katabatic winds are one of Antarctica's most distinctive features. Because cold air is denser than warm air, it literally flows downhill like an invisible river, accelerating as it descends from the high plateau toward the coast. In some valleys, these winds become trapped and focused, reaching speeds of 200 kilometers per hour, constant, unrelenting gales that can last for days. Early explorers described the sound as a freight train that never passes, a roar that makes sleep nearly impossible, and conversation requires shouting even when standing face to face. But here, in our relatively protected location on the plateau itself, the winds are kind. Tonight, there's barely a breeze, just enough movement to keep the air from becoming perfectly still, which can create dangerous temperature inversions where pockets of even colder air settle into low spots. I activate my radio to check in with the station, a safety protocol for anyone who's been outside for more than 30 minutes. Marcus answers immediately, his voice warm and slightly amused. "See anything interesting out there besides the light show?" "Found some bioluminescent organisms in a cryoconite patch," I tell him. "Collected samples for Chen to analyze tomorrow." There's a pause, then genuine excitement in his voice. "Seriously? That's remarkable. Get back here before you freeze yourself into the ice and become part of the core record." I smile inside my balaclava and sign off, beginning the walk back toward the station's lights. The aurora is slowly fading now, the curtains thinning and losing their intensity as the solar wind that powers them ebbs. This is how auroras usually end, not with a dramatic finale, but with a gentle diminishing, a slow return to darkness. As I walk, my mind drifts to thoughts of time and scale. The ice I'm walking on is flowing toward the coast at perhaps 10 meters per year, imperceptibly slow by human standards, but over geological time, it's enough to completely reshape the continent. The ice that's currently at the center of Antarctica will eventually make its way to the coast, break off as icebergs, and melt into the ocean, returning its ancient water to the sea. It came from hundreds of thousands of years ago. This is part of Earth's deep water cycle. Water evaporates from tropical oceans, travels through the atmosphere, falls as snow on Antarctica, accumulates for millennia, flows slowly to the coast, melts back into the ocean, and eventually evaporates again to continue the cycle. A single water molecule might spend 500,000 years locked in Antarctic ice between its time as ocean water and its return to the sea. During that time, civilizations could rise and fall, species could evolve and go extinct, continents could drift measurably across Earth's surface. Water is patient, ice is patient, Antarctica teaches patience. The station is closer now, and I can see Chen's silhouette in one of the windows. He's still awake, probably working on his research. Chen studies extremophiles in Antarctic soils, the scattered patches of exposed rock where conditions occasionally allow liquid water to exist for brief periods during summer. He's found bacteria that survive by going into a state of suspended animation during the harsh winter, their metabolism slowing to nearly zero, then reviving when conditions improve. One of his most interesting discoveries involves bacteria that produce antifreeze proteins, special molecules that bind to ice crystals and prevent them from growing. This allows liquid water to exist inside the bacterial cells even at temperatures several degrees below zero. These same antifreeze proteins have been found in Antarctic fish, in insects that overwinter in frozen states, even in some plants that survive extreme cold. Understanding how these organisms survive has practical applications beyond pure science. The antifreeze proteins are now used in frozen food preservation and in organ transplant medicine to prevent ice crystal damage. Some researchers are exploring their use in cryopreservation, the long-term storage of cells and tissues at ultra-low temperatures. If we could learn to preserve complex organisms in frozen states and revive them successfully, it could revolutionize medicine, enable long-duration space travel, even provide a kind of temporal escape hatch for endangered species. But more than the applications, what fascinates me is what extremophiles tell us about the fundamental nature of life. Life on Earth has conquered every available niche, adapted to every extreme environment. There are organisms that thrive at pH levels that would dissolve metal, temperatures that would boil water in normal pressure, pressures that would crush submarines, radiation levels thousands of times higher than what would kill a human, and here in Antarctica, cold that would freeze most organisms solid. This adaptability suggests that life is not fragile but incredibly robust, that given liquid water and an energy source, any energy source, life will find a way. This makes the search for life elsewhere in the universe feel less like searching for a needle in a haystack and more like searching for something that, while perhaps not common, is likely widespread given the right conditions. I'm nearly back to the station now, and I pause for one last look at the sky. The aurora has faded to a faint glow on the horizon, and now the stars are emerging in their full glory, with no moon currently visible and no light pollution for hundreds of kilometers in any direction. The stars appear in profusion that would astonish anyone who's only seen the night sky from a city or suburb. The Milky Way stretches overhead like a river of light, so dense with stars that it's impossible to distinguish individual points. They merge into a luminous band that bisects the sky. I can see the Magellanic Clouds, two irregular dwarf galaxies that orbit our own Milky Way galaxy, appearing as soft, glowing patches. These galaxies are our nearest neighbors, about 160,000 and 200,000 light-years away. Looking at them, I'm seeing light that left those galaxies long before modern humans evolved. The photons entering my eyes right now began their journey across intergalactic space when our ancestors were still sharing the planet with other species of humans, Neanderthals, Denisovans, Homo erectus. Those ancient humans looked up at these same galaxies, saw the same Magellanic Clouds, and wondered, as I do now, what they were seeing and what it all meant. I pull open the station door and step into the airlock, the warmth hitting me like a gentle wave. The transition is always striking, from the crystalline silence and cold of the exterior to the humming warmth and muted sounds of human habitation. I carefully remove my outer layers, brushing off ice crystals that have accumulated on my jacket, and hang everything on the designated hooks where they'll dry slowly overnight. Inside, the station is quiet but not silent. I can hear the low hum of the generators, the soft whoosh of the ventilation system circulating warm air, and from somewhere down the hall, the faint sound of classical music. Sarah must still be awake, reading to Beethoven or Brahms as she often does. Chen appears from the laboratory, his face lighting up when he sees me. "Marcus said you found something interesting." I pull the sample vial from my inner pocket, where I've kept it protected from my body heat by an insulated pouch. The bioluminescent organisms inside are no longer glowing. Bioluminescence usually requires the organism to be active and expending energy, and the cold has likely sent them into a dormant state. But under Chen's microscopes, and with the right conditions, we'll be able to revive them and observe their properties. Cryoconite on the surface, but with active bioluminescence, I explain. I've never encountered that before, not on the ice sheet itself. Chen takes the vial reverently, holding it up to the light. Even dormant, the sample is interesting. The dark sediment contains not just microorganisms, but also tiny particles of rock, organic matter, and cosmic dust. Cryoconite is a universe in miniature, a microhabitat where life persists against extraordinary odds. I'll start the analysis first thing tomorrow, Chen says. If these are producing light through bacterial luciferin-luciferase reactions, it could be a novel adaptation. Most bioluminescent bacteria use light for communication or attracting prey, but out here, he trails off, thinking, out here, it would have to serve a different function, possibly something to do with energy regulation or protection against UV radiation during the summer months. The mention of summer reminds me how different this place will be in a few months. Right now, we're in the transition period, not quite the deep winter isolation, but the perpetual twilight that precedes it. Soon, the sun will disappear entirely below the horizon and won't return for months. The temperature will plummet further, reaching -60 or 70 Celsius on the coldest nights. The aurora will become even more spectacular, with complete darkness providing the perfect canvas for the lights. But then, after winter, summer will return. The sun will circle the sky 24 hours a day, never setting, providing continuous daylight that can be disorienting in its relentlessness. The temperature will rise to almost freezing, and that slight warming will transform the landscape. Meltwater will appear in small streams on the ice surface, creating a network of channels and pools that exist only during the warmest weeks. Microscopic life will bloom in these temporary water sources: algae, bacteria, even tiny animals like tardigrades and rotifers that emerge from dormancy to feed and reproduce before the water freezes again. I've heard from colleagues who've spent summer seasons here that the continuous daylight affects human psychology in unexpected ways. Without the natural cycle of day and night, the body's circadian rhythms struggle to maintain their pattern. People find themselves staying awake for 20 or 30 hours at a stretch, then sleeping for 12, their internal clocks gradually drifting out of sync with the 24-hour day. Some find it liberating, a release from the tyranny of the clock. Others find it unsettling, missing the familiar rhythm of sunrise and sunset. Chen heads back to the lab with the sample, and I make my way to the common area, where I find Sarah curled up on the worn couch with a book and a cup of something steaming. She looks up and smiles. The aurora was beautiful tonight. I watched from the south window for a while. Sarah is our station geophysicist, studying the bedrock beneath the ice using seismic surveys. By setting off small controlled explosions or using specialized vibrators and analyzing how the shock waves travel through ice and rock, she can create three-dimensional maps of the continent's hidden topography. Antarctica isn't just a flat landmass under all that ice. It has mountain ranges, valleys, vast basins, even a canyon system longer and deeper than the Grand Canyon, all buried and invisible under kilometers of ice. Marcus mentioned you found bioluminescent organisms, she continues. That's the kind of discovery that makes months of routine work worthwhile. I pour myself tea from the communal pot, chamomile again, my favorite for evening, and settle into the opposite chair. It's a reminder that we're still learning about this place. After a century of Antarctic research, there are still surprises. Sarah nods, marking her place in her book. I was thinking about that today, actually. My latest seismic data shows what might be a geothermal hotspot under the ice about 80 kilometers from here. If I'm reading it correctly, there could be volcanic activity, not an eruption, but heat flow that's creating a subglacial lake we didn't know existed. This catches my attention fully. Volcanic activity? Under the ice sheet? Antarctica has more volcanoes than most people realize, Sarah explains, her enthusiasm for her subject evident. Mount Erebus, the southernmost active volcano on Earth, is just one of many. The West Antarctic Rift System is tectonically active, with hot mantle rock rising close to the surface. We've discovered at least 138 volcanoes beneath the ice, and probably many more we haven't found yet. The implications are significant. Volcanic heat beneath the ice sheet affects how the ice flows, creates pockets of meltwater that can lubricate the ice sheet's movement, and potentially creates habitable environments for extremophile communities. A subglacial lake warmed by geothermal heat would be even more hospitable to life than the pressure-melted water at the bottom of normal ice. If there's a geothermal lake there, I say, thinking aloud, and if it's been isolated long enough, it could host an entirely unique ecosystem. The organisms would have evolved independently from anything we've studied before. Sarah leans forward, animated now. Exactly. And here's what's particularly interesting. The seismic data suggests this lake might be quite large, perhaps 50 kilometers across and several hundred meters deep. The ice above it is thinning, probably from basal melting caused by the heat. If the melting continues, we might eventually be able to drill down to it, though that's decades away with current technology. The idea of a vast, warm lake hidden beneath the ice, possibly teeming with life forms that have evolved in complete isolation for millions of years, is almost overwhelming. It's like having an alien world right here on Earth waiting to be explored. Every subglacial lake is a time capsule and a laboratory, showing us what's possible for life under conditions that might exist elsewhere in the solar system. There's something else, Sarah continues, pulling out her tablet and calling up a three-dimensional visualization of the bedrock topography. The lake sits in a basin that's actually below sea level. Like most of West Antarctica, the weight of the ice has pushed the bedrock down. But the basin is ring-shaped, with elevated terrain around the edges and a central peak. That's the signature of an ancient impact crater. I stare at the image, processing what she's saying. An asteroid impact? Probably about 1 kilometer in diameter, based on the size of the crater. It hit Antarctica sometime in the distant past. I'd need to get samples of the rock to date it precisely, but the morphology is unmistakable. And now there's a geothermal lake sitting right in the center of it. This adds another layer to the story. Impact craters, especially ancient ones that have been worn down by erosion or buried by sediment and ice, are windows into Earth's violent past. Our planet has been struck countless times by asteroids and comets throughout its history. Most of the craters have been erased by plate tectonics, erosion, and geological recycling. But in stable, protected places like beneath the Antarctic ice sheet, they can survive for hundreds of millions of years. The dinosaurs were famously wiped out by an asteroid impact 66 million years ago. The Chicxulub impactor that struck what is now Mexico's Yucatan Peninsula. The impact released energy equivalent to billions of nuclear bombs, threw up so much dust and debris that it blocked out the sun for years, triggered worldwide fires and tsunamis, and led to the extinction of about 75% of all species on Earth. But it also, paradoxically, created opportunities. The extinction of the dinosaurs allowed mammals to diversify and eventually gave rise to primates and humans. Impact craters can be geologically active, I say, following the thread. The impact fractures the bedrock, creates pathways for heat and fluids to move through the crust. Combined with the insulating effect of the ice above, you could have a stable geothermal system that's persisted for millions of years. Sarah nods enthusiastically. And if organisms colonized that lake early in its history, they've had millions of years to evolve in isolation. The lake would be its own evolutionary experiment, completely separate from the rest of Earth's biosphere. We sit in companionable silence for a moment, both contemplating the hidden world beneath our feet. This is one of the great privileges of being a scientist, not just learning facts, but participating in the process of discovery, being among the first humans to know something new about the universe. Every answered question opens up new questions, deeper mysteries. The station creaks slightly as it adjusts to the cooling night temperatures outside. These sounds used to unsettle me when I first arrived, but now they're comforting, familiar. The station is a small bubble of warmth and life in one of the most inhospitable environments on Earth, but it's proven remarkably reliable. The design is based on decades of Antarctic engineering experience, elevated on stilts to prevent snow burial, aerodynamic to minimize wind resistance, heavily insulated with redundant systems for heat, power, and life support. I should sleep, Sarah says, though she doesn't move immediately. We have the ice core processing session starting at 8 tomorrow, and I want to be alert for it. Tomorrow, we'll be examining cores from various depths, looking for volcanic ash layers that can help us correlate climate events between different drilling sites. Volcanic eruptions inject massive amounts of sulfur dioxide and ash into the stratosphere, where it can circulate globally before settling out over months or years. These ash layers appear in ice cores all over the world, providing perfectly synchronized time markers. If we find the same volcanic signature in cores from Antarctica, Greenland, and high-altitude ice caps in the tropics, we know those ice layers are the same age, even if they're separated by thousands of kilometers. One of the most useful volcanic markers is from the Tambora eruption in Indonesia in 1815, the largest volcanic eruption in recorded history. It ejected so much material into the atmosphere that the following year, 1816, became known as the year without a summer. Crops failed across the northern hemisphere, causing widespread famine. Snow fell in June in New England. Temperatures in Europe were so cold that Mary Shelley, confined indoors during what should have been a pleasant summer vacation in Switzerland, passed the time by writing Frankenstein. That eruption killed tens of thousands of people directly and hundreds of thousands more through the subsequent famine and disease. Yet we can trace its global impact precisely through ice cores, seeing the exact layers where Tambora's sulfur and ash settled into the accumulating snow in Antarctica, Greenland, and elsewhere. The ice remembers what happened, preserving the evidence long after human memories fade and written records crumble. Sarah finally stands, stretching. Good night. Don't stay up too late thinking about ancient impact craters and hidden lakes. I smile. No promises. After she leaves, I remain in the common area, finishing my tea slowly. The station is settling into its night routine, lights dimming automatically in unoccupied areas to conserve power and help maintain our circadian rhythms despite the unchanging twilight outside. I can hear someone snoring softly from the sleeping quarters, a homey sound that reminds me this is a place where humans live, not just work. My thoughts drift to the journey that brought me here, the years of study and training, the grant applications and research proposals, the gradual narrowing of focus that eventually led to Antarctica. I didn't always want to be a glaciologist. As a child, I wanted to be an astronaut, drawn to the mystery of space and distant planets. But somewhere along the way, I realized that Earth itself held mysteries just as profound, and they were more accessible, more immediate. Antarctica became my space exploration, my alien world. Here, I could study environments similar to those on Mars or Europa without leaving Earth. I could examine life at its limits, climate processes at their extremes, geological timescales made visible in ice. And unlike space exploration, where rovers and probes transmit data from millions of kilometers away, here I could experience it directly, touch the ice, breathe the cold air, witness the aurora with my own eyes. I think about the people who first came to Antarctica, the explorers of the early 20th century who traveled here with wooden ships and primitive equipment, facing dangers we can barely imagine now. Ernest Shackleton's expedition in 1914, when his ship Endurance became trapped in pack ice and was slowly crushed, forcing the crew to camp on floating ice for months before making a desperate boat journey to South Georgia Island. A navigation feat accomplished with just a sextant and chronometer across some of the world's most dangerous seas. They all survived, a testament to leadership and human endurance. Robert Falcon Scott's tragic expedition to the South Pole in 1912, reaching their destination only to find that Roald Amundsen had beaten them by 5 weeks, then perishing on the return journey, their bodies and journals found 8 months later, preserved perfectly in the cold. Scott's final diary entries are haunting in their dignity and resignation, describing the worsening conditions, the failing health of his companions, his regret at not seeing his wife and son again. Those explorers contributed immensely to our knowledge, mapping the continent, collecting geological and biological samples, recording weather observations. But they were also driven by something less tangible, the human need to explore, to test ourselves against the unknown, to stand in places no one had stood before. That impulse is still alive today, redirected from geographical discovery to scientific discovery, from mapping blank spaces on a chart to understanding the mechanisms that govern our planet. I finish my tea and rinse the cup, placing it in the drying rack. The station's kitchen is compact but well designed, with everything we need and nothing superfluous. Life here teaches you to distinguish between needs and wants, between what's essential and what's merely comfortable. We have enough food for months, varied enough to prevent boredom, but nothing extravagant. Fresh produce is rare. Mostly we eat freeze-dried or canned foods, with fresh items only when a supply flight arrives. Yet despite the simplicity, or perhaps because of it, there's a satisfaction to life here that's hard to explain to people back in the world of abundance and constant choice. Here, every supply flight is an event. Every fresh apple is appreciated in a way that's impossible when you have unlimited access to supermarkets. The restrictions create a kind of mindfulness, an awareness of what we have and how we use it. I make my way to my quarters, a small private room with a bunk, a desk, storage space, and a window. The window is my greatest luxury. Not everyone has one, and I'm grateful for it every day. Through it now, I can see the landscape of ice stretching away under starlight, the horizon barely distinguishable from the sky in the perpetual twilight. I sit at my desk and open my journal, a habit I've maintained throughout my time here, not a scientific journal, but a personal one, recording thoughts and observations that won't appear in any research paper. Writing by hand has become a small ritual, the physical act of forming letters connecting me to the moment in a way that typing on a computer doesn't quite achieve. Today's entry begins with the aurora, describing the colors and patterns, the rare appearance of Steve, the corona formation that made the sky look like a vast spiral. I write about finding the bioluminescent organisms, my conversation with Sarah about the hidden lake and impact crater. But I also write about the feeling of standing alone on the ice under that immense sky, the sense of being small in a way that's comforting rather than frightening, part of something much larger than myself. Antarctic researchers have a high rate of what psychologists call flow states, those moments when you're so absorbed in an activity that time seems to disappear, when challenge and skill are perfectly matched, when you feel simultaneously focused and relaxed. Part of it is the work itself, which requires attention and provides meaning. But part of it is the environment, the absence of ordinary distractions and demands, the simplicity of life pared down to essentials. There's also something about the landscape itself that encourages contemplation, the vastness, the purity of form, ice and sky, white and blue, with minimal variation. It's almost abstract, like a painting reduced to its fundamental elements. Your mind has space to wander, to make connections, to think deeply without the constant interruptions of modern life. I write about time, a subject that's been occupying my thoughts lately. Human perception of time is so subjective, so malleable. A day here can feel both endless and instantaneous. Endless because the unchanging light makes hours blend together. Instantaneous because the work is engaging and meaningful. But the ice teaches a different kind of time, geological time measured in millennia and eons, where human lifespans are barely noticeable. The ice I'm sitting on fell as snow when Rome was an empire, when the pyramids were already ancient, when humans had just begun to build cities and develop writing. But that's recent ice, surface ice. Deeper down are layers from the ice ages, from times when the Earth's climate was radically different, when sea levels were 400 feet lower because so much water was locked up in ice, when you could walk from Asia to North America across the Bering Land Bridge, and deeper still, ice from warm periods between glaciations, when temperatures were higher than today, when forests grew at latitudes that are now tundra, when hippopotamuses wallowed in rivers in what is now England. The ice records all of it, alternating bands of thick accumulation during wet periods and thin layers during dry periods, chemical signatures that reveal temperature and atmospheric composition, dust particles that tell us about wind patterns and volcanic activity. Understanding these cycles is crucial for predicting future climate. Earth's climate has never been static. It has oscillated between cold glacial periods and warm interglacials for at least the past 3 million years, driven primarily by variations in Earth's orbit and axial tilt. These Milankovitch cycles, named after Serbian mathematician Milutin Milankovic, who calculated them in the 1920s, affect how much sunlight reaches different parts of Earth at different seasons. 3 main cycles interact. The eccentricity of Earth's orbit changes over roughly 100,000 years, making the orbit more or less elliptical. The tilt of Earth's axis varies between 22.1 and 24.5 degrees over 41,000 years, affecting the severity of seasons. And the axis itself wobbles like a spinning top over 26,000 years, changing which hemisphere is tilted toward the sun during which season. These cycles don't cause huge changes in total solar energy reaching Earth, just a few percent variation, but they're amplified by feedback mechanisms involving ice sheets, ocean circulation, atmospheric carbon dioxide, and vegetation. When orbital conditions favor cooler summers in the northern hemisphere, snow that falls during winter doesn't completely melt. It accumulates year after year, compressing into ice, forming glaciers that gradually expand. Ice reflects sunlight back to space, cooling the planet further, allowing more ice to form. A positive feedback loop. Carbon dioxide gets absorbed by cooler oceans and locked away, removing a greenhouse gas from the atmosphere and accelerating cooling. Forests retreat, replaced by grasslands and tundra that reflect more light than dark trees. The system can remain in this cold state for tens of thousands of years until orbital conditions shift enough to trigger warming. Then the process reverses. Ice melts, exposing darker ground that absorbs more heat. Oceans release dissolved carbon dioxide. Forests expand poleward. Within a few thousand years, rapid by geological standards, Earth transitions from ice age to interglacial warmth. We're currently in an interglacial period that began about 11,700 years ago, called the Holocene. Without human influence, the planet would naturally be heading slowly toward the next ice age, though that wouldn't begin in earnest for thousands of years. But human activities have altered the trajectory by adding enormous amounts of greenhouse gases to the atmosphere through burning fossil fuels, fundamentally changing the energy balance. I close my journal, these thoughts feeling too heavy for the peaceful quiet of the evening. The science is clear, the implications profound, but tonight I want to simply be present in this remarkable place, grateful for the opportunity to be here, to witness beauty and contribute to human knowledge. I prepare for sleep, changing into thermal sleeping clothes and sliding into my sleeping bag. The bag is rated for extreme cold, though the room itself is kept comfortably heated. Outside my window, the stars wheel slowly across the sky as Earth rotates. From here, at high southern latitude, the celestial South Pole is nearly overhead, and the stars appear to circle it in great arcs. Unlike the North, which has Polaris, the North Star, sitting conveniently near the celestial pole, the South Pole has no bright star marking it. Instead, the Southern Cross constellation points toward it, with the long axis of the cross directing your eye to an empty patch of sky where the South Celestial Pole resides. Early navigators learned to find south by locating the cross and following its pointer, essential knowledge for sailing the southern oceans. I think about navigation, about how humans have always oriented ourselves using the sky. Before GPS, before compasses even, we had the stars. Different cultures developed sophisticated understanding of celestial motion, using it to cross oceans, deserts, and trackless plains. Polynesian navigators could island hop across thousands of miles of Pacific Ocean by reading stars, swells, and seabirds. Arab astronomers created detailed star catalogs and instruments for celestial navigation. Aboriginal Australians encoded astronomical knowledge in songlines that mapped both Earth and sky. That knowledge is still encoded in our language. Orientation itself comes from orient, meaning east, because maps were traditionally aligned with east at the top. Disaster comes from Latin roots meaning bad star, reflecting a time when people believed celestial events directly influenced earthly affairs. We're only a few generations removed from a world where knowing the night sky was a practical necessity, not just an aesthetic pleasure. Here in Antarctica, far from city lights, the sky appears as our ancestors saw it, vast, crowded with stars, the Milky Way a luminous river dividing the darkness. On clear nights like this, you can see why ancient peoples invented mythologies to explain it, weaving stories that connected the patterns above to the dramas of human life below. The stars became gods, heroes, animals, eternal reminders of stories that bound communities together and passed knowledge across generations. My breathing slows, deepens, falling into the rhythm of approaching sleep. The sleeping bag is warm, my body relaxed after the day's activities and the walk in the cold. I feel the pleasant heaviness of fatigue settling over me, that transition state between waking and sleeping where thoughts become dreamlike, less linear, more associative. Images drift through my mind, the spiral aurora corona, the glowing organisms in the cryoconite, Sarah's maps of hidden topography beneath the ice, the ancient impact crater now filled with a geothermal lake, all of it interconnected, part of Earth's vast system of energy and matter constantly cycling, transforming, creating the conditions for complexity and life. I drift into sleep, but my dreams are vivid, filled with ice and light. I'm walking across the plateau, but the ice beneath my feet is transparent, perfectly clear, and I can see down through it, through hundreds of meters, through thousands of meters, through the entire depth of the ice sheet. I can see the layers like pages in a book, each one distinct, each one holding its history. Some layers contain a volcanic ash, dark smudges in the white. Others have tiny air bubbles that catch and reflect light like stars trapped in ice. As I walk, I realize I'm moving through time as well as space. Each step takes me further into the past. The ice around me grows older, the layers beneath representing epochs before human civilization, before agriculture, before language. I see the last ice age in the layers, a time when glaciers covered much of North America and Europe, when the ancestors of modern humans were hunter-gatherers following herds across vast grasslands. Deeper still, and I'm in a time before humans existed at all. The ice remembers a world of megafauna, giant ground sloths, saber-toothed cats, woolly mammoths traversing frozen steppes. The climate oscillates in the ice record, warm periods and cold periods alternating like the breathing of the planet itself. In the dream, I can somehow read the ice directly, understanding its chemical signatures intuitively. I see carbon dioxide concentrations rising and falling in rhythm with temperature, never exceeding certain bounds for hundreds of thousands of years. I see methane levels responding to changes in wetlands and permafrost. I see oxygen isotopes recording the advance and retreat of ice sheets across continents. Then something changes in the ice. The most recent layers, representing just the last century or two, show a sharp departure from all the patterns that came before. Carbon dioxide levels spike upward, rising faster than at any point in the ice record. Methane climbs steeply. The chemical balance that persisted for hundreds of millennia suddenly shifts, and I understand with dream clarity that I'm looking at human civilization written in ice, our species' transformation from a marginal presence to a geological force. But the dream doesn't feel ominous or frightening. Instead, there's a sense of responsibility, of witnessing something important. The ice is still recording, still preserving the evidence, still offering its knowledge to anyone willing to read it carefully. And humans, the same species that caused these changes, are also the ones studying them, understanding them, working to comprehend the system we've altered. The dream shifts, and now I'm no longer on the ice surface but beneath it, in the hidden geothermal lake Sarah described. The water is surprisingly warm, perhaps near freezing at the surface, but warmer as I descend toward the heat source below. The lake is vast, its boundaries disappearing into darkness, lit only by a dim glow I can't identify. Then I realize the glow is coming from life itself. Colonies of bioluminescent bacteria coating the rocks, creating a constellation of blue-green lights in the depths They're producing light down here where no sunlight has penetrated for millions of years. Light that serves no purpose except perhaps to mark territory or signal to others of their kind. It's beautiful and strange, this hidden world that exists in complete isolation from the surface. Strange fish-like shapes move through the water, not actual fish, but something else. Creatures that have evolved in total darkness and adapted to this unique environment. They're pale, almost translucent, with no eyes because eyes would be useless here. Instead, they navigate by sensing chemical gradients and water movements, feeding on bacteria and organic matter that rains down from above or seeps up from below. In the dream, I understand that this lake has existed for perhaps 10 million years, isolated beneath the ice since Antarctica glaciated, and life has had that entire time to adapt and diversify in its confines. The organisms here are related to surface life. They share the same basic biochemistry, the same genetic code, but they've diverged, evolved unique solutions to the challenges of living in perpetual cold and darkness. I swim deeper, though I have no sense of being cold or needing to breathe. Dream logic allows me to explore freely. The bottom of the lake appears covered in a thick mat of microbial growth, and beneath that, the rock of the impact crater floor. The heat is stronger here, rising from fractures in the bedrock where water circulates deep into the crust and returns heated by Earth's internal warmth. Around these thermal vents, life is most concentrated. Complex structures made of minerals precipitate from the hot water, creating chimney-like formations that tower several meters high. These are similar to hydrothermal vents in the deep ocean, and like those ocean vents, they support dense communities of organisms. Mats of bacteria coat every surface, their metabolism powered by chemical energy from sulfur compounds and hydrogen in the vent fluids. Larger organisms live among the vents, perhaps evolutionary descendants of species that lived in Antarctica's lakes before glaciation, that survived the Ice Age by adapting to this refuge. Or perhaps they're descended from microorganisms that were already adapted to deep crustal environments and found their way here through cracks in the bedrock. Either way, they represent millions of years of isolated evolution. The dream begins to fade, images becoming less distinct, and I'm rising back through the water, through the ice, returning to the surface and to consciousness. But the sense of wonder remains, that feeling of having glimpsed something profound and ancient. I wake slowly, gently, the way one wakes after deep, restful sleep. The room is dim, the window showing the same twilight blue that seems eternal here. I check my watch. I've slept for 9 hours, longer than usual, and I feel genuinely refreshed. The dreams linger in my memory with unusual clarity, vivid enough that I lie still for several minutes, reviewing them, trying to hold on to the images and feelings before they fade the way dreams usually do. There's something about sleep in Antarctica that's different from sleep anywhere else I've experienced. Perhaps it's the extreme quiet, the absence of the background noise that exists everywhere in the populated world. No traffic sounds, no airplanes overhead, no neighbors, no hum of distant machinery except the station's own systems. Or perhaps it's the unchanging light, the way the body surrenders to sleep, not because darkness signals it, but because genuine fatigue makes it necessary. I rise and dress, pulling on layers against the chill that accumulates in rooms overnight despite the heating. The station is awake. I can hear voices from the common area, smell coffee brewing, the familiar sounds of morning routine. When I emerge from my quarters, I find most of the team already gathered, discussing the day's plans over breakfast. Chen looks up and grins. Your bioluminescent organisms are even more interesting than we thought. I was up until midnight analyzing them. They're producing light through a luciferase reaction, but the luciferin substrate is novel. I've never seen this particular chemical structure before. I'll need to sequence their DNA to understand where they fit in the tree of life. This is exciting news. Every novel organism we discover expands our understanding of life's possibilities, reveals new biochemical pathways, potentially offers practical applications. Many important drugs and industrial enzymes have been discovered by studying extremophiles. Organisms living in extreme environments often produce unique chemicals that help them survive, and those chemicals sometimes have properties useful to humans. Marcus is reviewing data from the automated weather stations on his laptop. We're expecting a weather system to move through in about 3 days. Not a major storm, but winds will pick up to maybe 40 knots with some snow. We should plan any outdoor work accordingly. Weather systems in Antarctica can be challenging to predict because there are so few observation stations, leaving vast areas unmonitored. Satellites help, but they can't capture everything, especially near-surface conditions. A storm that seems modest by Antarctic standards, winds of 40 or 50 knots, would be significant anywhere else. But here we're accustomed to wind and have procedures for working safely in it. Sarah is already suited up for outdoor work, preparing to deploy seismic sensors at the site where she suspects the geothermal lake exists. I want to get more detailed data before the weather deteriorates, she explains. If the readings confirm what I think is there, we can include it in the next season's drilling proposals. Imagine being the first to sample a lake that's been isolated for 10 million years. The thought sends a thrill through me. This is why we're here, not just to study what we know exists, but to discover what we don't yet know, to push the boundaries of human knowledge incrementally forward. Each discovery, each new data point, each novel organism or unexpected geological feature adds to our collective understanding. After breakfast, I joined Sarah in preparing for the field work. We'll take one of the station's snowmobiles to the site, about 15 kilometers away, and spend several hours deploying and calibrating equipment. It's the kind of task that requires concentration and care, but also offers time for thought, for conversation, for experiencing the landscape. The sky is clear as we depart, the same endless twilight that has become familiar. The snowmobile's engine breaks the silence, a mechanical sound that feels almost transgressive in this quiet place, but necessary. We follow GPS coordinates and marker flags from Sarah's previous reconnaissance, traveling across ice that looks uniform but actually has subtle variations. Areas where wind has sculpted the snow into patterns, places where the ice is smoother or rougher. As we travel, Sarah tells me about her career path, how she became interested in geophysics, the research projects that led her eventually to Antarctica. Like me, she didn't start out planning to work at the bottom of the world, but Antarctica has a way of drawing certain people, those who are comfortable with isolation and extreme environments, who find beauty in austerity. There's something addictive about it, she says over the radio. We're wearing full face protection against the cold, making direct conversation difficult. Every time I leave, I start planning my return before I've even gotten home. The rest of the world feels too crowded, too noisy, too complicated. I understand exactly what she means. Antarctica offers a clarity that's rare. Clarity of purpose, clarity of environment, clarity of thought. The challenges are real but straightforward. Stay warm, stay safe, do good science. No political complications, no traffic jams, no advertisements, no social obligations beyond the small community of people you share the station with. We reach the site and begin the careful work of deploying seismic sensors. Each one must be placed precisely, leveled carefully, connected to the data logger that will record vibrations traveling through the ice and rock. Sarah sets off small explosive charges at measured distances, and the sensors record how long the shock waves take to reach them and how they're modified by traveling through different materials. Ice transmits seismic waves at one speed, rock at another, water at yet another. By analyzing the timing and characteristics of waves that have traveled different paths, Sarah can create a three-dimensional picture of what lies beneath us. It's like ultrasound imaging, but on a geological scale. The work takes hours, methodical and precise. Between sensor deployments, we stand in the vast quiet, and I find myself thinking about the hidden lake that might exist beneath us. A dark, warm refuge in the midst of all this ice, harboring life that has evolved in isolation for unimaginable spans of time. It's a reminder that Earth still holds secrets, still has places we haven't explored, phenomena we don't yet understand. As we work, the light begins to shift subtly. The sun, which has been making its lazy circle near the horizon, dips slightly lower, and the colors in the sky deepen. Lavenders and roses and deep purples spreading across the western horizon. In a few weeks, the sun will disappear entirely for the winter, but for now, we're in this transition period, this slow dimming. Sarah completes the final calibration and checks the data logger. Perfect. These sensors will record continuously for the next 6 months. By the time we retrieve them, we'll have enough data to confirm or refute the lake hypothesis definitively. We pack up the equipment and prepare for the return journey. As I'm securing the gear on the snowmobile, I notice something on the horizon, a faint vertical column of light rising from the ice surface into the sky. At first, I think it might be a distant aurora, but it's too localized, too steady. Light pillar, Sarah says, following my gaze. Ice crystals in the air catching the sun's light. They're quite rare. You need perfectly calm conditions and just the right type of ice crystals suspended in the air. We stand together, watching the phenomenon. The pillar shifts subtly, brightening and dimming as the concentration of ice crystals changes, but it remains vertical, a column of soft, golden pink light connecting earth and sky. It's another of Antarctica's quiet miracles, the kind of thing that would be impossible to explain adequately to someone who hasn't been here. The journey back to the station is peaceful. I feel the deep satisfaction that comes from a day of productive work in an extraordinary place. The landscape slides past, white and blue and endless, and I think about how many days like this I have left before my rotation ends. Not enough, never enough. When we arrive back at the station, the rest of the team is gathered in the common area, and there's an unusual energy in the air. Chen sees us and waves us over excitedly. You need to see this. The DNA sequencing results came back from your bioluminescent sample. He pulls up data on his laptop. Complex sequences of genetic code that mean little to me, but clearly mean a great deal to him. These organisms are ancient. Based on their DNA, they diverged from their nearest known relatives roughly 30 million years ago. They've been evolving independently since Antarctica glaciated, probably surviving in tiny pockets of liquid water within the ice or in subglacial environments. 30 million years of independent evolution. These microorganisms have been quietly living and adapting through the entire history of Antarctic glaciation, through the rise and fall of countless species elsewhere on Earth, through dramatic climate changes and geological upheavals. And they've developed a unique form of bioluminescence, producing light in one of the darkest, coldest places on the planet. There's more, Chen continues. The luciferin they produce has unusual properties. It's extremely stable at low temperatures and requires very little energy to generate light. If we can synthesize it, it could have applications in low-temperature biochemistry, maybe even in developing new tools for studying extremophiles on other worlds. This is the beauty of basic science. You never know where discoveries will lead. We came to Antarctica to study ice and climate, but we've found novel life forms that might contribute to fields we hadn't even considered. Every answer generates new questions. Every discovery opens new paths of inquiry. As evening settles over the station, though evening is somewhat arbitrary in the perpetual twilight, I find myself back in the observation dome, the place where this day's journey truly began. The aurora has not yet appeared tonight, but the stars are brilliant, and the ice reflects their light in subtle ways that create an almost ethereal atmosphere. I think about the layers of time compressed beneath me, the ice holding records of Earth's past, the hidden lakes preserving ancient ecosystems, the bedrock bearing scars of impacts from space. All of it interconnected, all of it part of the vast story of this planet and its place in the cosmos. Antarctica has taught me patience. Not everything reveals itself immediately. Some truths take time to understand, require persistence and careful attention. The ice cores we extract today might not yield their most important insights for decades, when new technologies allow us to analyze them in ways we can't yet imagine. The organisms we discover might have applications we won't recognize for years. But that's the nature of exploration in science. You move forward with incomplete knowledge, driven by curiosity and the belief that understanding matters, that knowledge has intrinsic value even when practical applications aren't immediately apparent. I feel profoundly grateful to be here, to be part of this work, to witness the beauty and complexity of this remarkable place. Tomorrow, there will be more work, ice cores to process, data to analyze, equipment to maintain. The weather system Marcus predicted will arrive in a few days, bringing wind and snow. Eventually, the sun will disappear for winter, the temperature will plummet further, and we'll be truly isolated. But tonight, I'm simply here, present in this moment, breathing cold air and watching stars wheel overhead, a small conscious being on a vast planet, participating in the ancient human endeavor of trying to understand the world we inhabit. The ice beneath me holds stories spanning hundreds of thousands of years. The organisms Chen is studying carry the history of 30 million years in their DNA. The light from the stars overhead began its journey decades or centuries ago, traveling across space to reach my eyes in this precise moment. Everything is connected across time and space. The solar wind that creates auroras, the ice that records climate, the life that adapts to extremes, the curiosity that drives humans to explore and understand. We're all part of the same vast system, the same ongoing story of matter and energy organizing itself into ever more complex forms, creating beauty and meaning in an otherwise indifferent universe. I take a deep breath of the cold, pure air and feel complete peace settle over me. This is enough. This moment, this place, this work. The privilege of being here, of contributing in some small way to human knowledge, of witnessing wonders that few will ever see. It's more than enough. Outside, the ice continues its slow flow toward the sea. Stars continue their ancient patterns. Life continues to adapt, persist, and surprise us. And I continue to watch, to learn, to be present in this remarkable landscape at the bottom of the world, where time itself seems frozen, yet everything is always changing, where isolation brings connection, and where the coldest place on earth offers some of the warmest moments of wonder I've ever experienced. If you've enjoyed this journey through the frozen library of Antarctica, through time and ice and the quiet wonders of our remarkable planet, please consider subscribing to our channel. Each story we create is an invitation to slow down, to wonder, and to drift peacefully into rest. Your support helps us continue bringing these gentle, scientifically inspired sleep journeys to you. Sleep well, and thank you for exploring with us.